Hey BC Cal kids, this video is over P series, harmonic series, and the alternating series. We may add in a couple of extra things, well, we'll see. All right, so in this paragraph, we talk about an improper integral. An improper integral is used to justify why the P series and subsequently the harmonic series converge or diverge. An improper integral is just an integral where one of the limits is either negative infinity or positive infinity. You work them like you do any definite integral. You just integrate and substitute in the limits. We'll see the notation when we do example one. You know what, actually, before we get started, so the integral test is used to justify the convergence or divergence of series if you can't use the geometric series test or these other tests that we have for convergence and divergence. We'll talk about that when we finish the first example. So we have this example from the integral from 1 to infinity of e to the negative x dx. So the proper way to do this is the limit as b approaches infinity of the integral from 1 to b of e to the negative x dx. Now, the reason we use b is that when we have a definite integral, the lower limit is a and the upper limit is b. And so since b is the one that's the infinity, we just replace the infinity with a b. Now from here, we just integrate like we generally would integrate. The antiderivative of e to the negative x is e to the negative x divided by the derivative of negative x, which is -1. So dividing by -1 is the same as multiplying by -1. Excuse me, I forgot my limit. So we need the limit as b approaches infinity of negative e to the negative x evaluated from 1 to b. Now, again, the reason we get this negative is because when you integrate a linear function, when you integrate a function whose, in this case, exponential, since the exponent is a linear function, you get e to that linear function and you divide by the slope of that linear function. So we get e to the negative x divided by -1, which is the same as multiplying by -1. So the rewrite that you could do is the limit as b approaches infinity of -1 over e to the positive x evaluated from 1 to b. And so if we're doing this as the limit as b approaches infinity of -1 over e to the b minus -1 over e, then when b goes to infinity, since e is larger than 1, what we learn with geometric series is that if the ratio is less than 1, the limit is going to converge to 0. So in this case, the limit for this first fraction is going to be 0. So we get 0 plus 1 over e, and that's our final answer. So because we got an answer with this infinite limit, we would say that this integral is convergent. And what that would mean is over here, say we had a series where we had the series from n equals 1 to infinity of e to the negative n. Then because this integral is convergent, so is this series. Because an integral is just like when we did definite integrals initially, we found out that a definite integral is just a sum of a bunch of infinitely small rectangles. And so since this series is also a sum, since this sum, which is an integral, is convergent, this series that could be represented by an integral is also going to be convergent. It works in both directions. So if we get an answer that's divergent, then this series is also going to be divergent. So for example 2, we have the antiderivative of 1 over x squared dx, and we have a limit of -infinity and a limit of 1. Now, we have a point of discontinuity in this interval. X can't equal 0. But 0 is a part of our interval. So what we're going to do is rewrite this as the integral from negative infinity to 0 of 1 over x squared plus the integral from, I forgot the dx, but it's not terribly important. 1 over x squared. Now we will put in a dx. You know what? Just slide in right here. So when we integrate this, so this is x to the negative 2. That's x to the negative 2. Now, we don't have to include the limits. We can just internalize that we need to do a limit when we get to the end. I like doing that. It cleans up the process a little bit, and it's just notation. So when we integrate this, we're going to get, so remember, this is x to the negative 2 in both instances. So when we integrate x to the negative 2, we get x to the negative 1 evaluated from, in the first case, negative infinity to 0, and then plus, excuse me, the same thing, plus x to the negative 1, and then evaluated from 0 to 1. Now, in both instances, you can rewrite this to be, this should be x to the negative 1 divided by negative 1. So both of these should be a negative. So we'll get negative 1 over x evaluated from negative infinity to 0 minus 1 over x evaluated from 0 to 1. Now on Desmos, I pulled up the graph of 1 over x just in case you forgot how the graph looks. So when x goes to negative infinity, what happens is the lower limit is going to become 0. So we end up with negative 1 divided by, in this place, we're going to put b for a moment. So negative 1 over b minus negative 1 over essentially negative infinity. Now, again, this is improper notation, but it just helps illustrate what we have going on. So then minus, then when we substitute in 1 and 0 for the second integral, we're going to have minus 1 over 1 minus 1 over, in this case, we're going to have a, and we'll see what we get. So b is some number that's really close to 0. Now, we can't actually equal 0 because we divide by 0, but since we're approaching 1, if we approach 0 from the left, then what happens is we get a very, very large number. So this first thing is going to be infinity minus, then negative 1 divided by a very large number is going to be 0. Then we get minus 1 and minus. Now, a is 0, but between 0 and 1, we're approaching 0 from the right. So if we look at the graph of 1 over x, then when you approach 0 from the right, what happens is the value gets very, very large when you get close to 0, when you get close to the y-axis. So this is going to be 0 as well. And this is going to be infinity. And so what we get is this integral is divergent because of these infinities. Now, we could have stopped when we got this infinity, but this series is going to be divergent. So, for example, 2 is almost the same thing, except, you know what? To make this look like something that we would do for a series, let's change this to be from 1 to infinity. We're going to get the same answer up to a negative. So now we don't have to worry, like in example 2, we have to worry about this point of discontinuity at 0. But in example 2 star, we're past the point of discontinuity, x equals 0. We're starting at 1. So we're still going to integrate this like we would. This is going to be negative x to the negative 1 evaluated from 1 to infinity. So that's going to be negative 1 over, we're going to put in quotes, infinity minus negative 1 over 1, which equals 1, because this first fraction is going to be 0 because you have negative 1 divided by a large number, which is going to be 0. So we get 0 plus 1, which just equals 1. Now, again, we're just using this as shorthand for all of this. Now, if you wanted to, you could say that this is the limit as b approaches infinity of -1 over x evaluated from 1 to b, and then that would be the limit as b approaches infinity of -1 over b minus -1 over 1, which again, when b goes to infinity, this fraction is going to be 0 and this fraction is going to turn into a +1. So we get 1 either way. But I just like the shorthand so we don't have to do all of this. So because this limit converges to 1, if we see a series, where we have from n equals 1 to infinity of 1 over n squared, then this is going to be convergent. We're going to have convergent because the integral converges. And that leads us into the P series. Now, P series is just a series where you have 1 over n to a positive integer. So, well, not positive integer, we're going to say positive, just a positive number. Now, generally, we're going to see like rational numbers or integers, but really P just has to be some positive number. But because we're generally dealing with sequences, we really only work with rational numbers or integers. So through improper integrals and the integral test, we can show that a P series only converges when P is greater than 1. This is the harmonic series, the case where P equals 1, where the exponent is 1. This is divergent. And it goes against a lot of what we think, because as you continue to add values to the sequence, the series, each value is smaller. So it would seem that this series has an upper bound. If you look around on the internet, you can find a pretty cool proof that shows that even though every value that you add is progressively smaller, that you can group together enough terms to show that a certain group of terms adds up to be a half, and you can just infinitely add a half over and over again, which means that the series has to be getting larger. This diverges very slowly, but it is divergent, and it's divergent because P equals 1. And again, that's the harmonic series when P equals 1. So P series don't involve any work at all. You can just look at the series, and if the exponent is greater than 1, the series is convergent. If the exponent is less than or equal to 1, the series is divergent. So, I mean, this is what we have. We have the P series. It converges if P is greater than 1, diverges if P is less than or equal to 1. So now, again, you can use the integral test to justify any of these, but we're not going to do that. So in the case from n equals 1 to infinity, so n equals 1 to infinity of 1 over n cubed, this is going to be convergent because P equals 3. In the case of example 4, so we have 1 plus 1 over square root 2 plus 1 over square root 3. And so we probably can rewrite this to be the sum from n equals 1 to infinity of 1 over the square root of n. So another rewrite you could do is the sum from n equals 1 to infinity of 1 over n to the 1/2. And in this case, we're going to get divergent, and the answer is going to be because P equals 1/2. Now, again, if you did the integral test, you'd end up with 2n to the 1/2. And then when n goes to infinity, you're going to get a progressively larger square root. So because that integral diverges, so will this series. For example 5, we have -1 minus 1/2 minus 1/3 minus 1/4. So it seems as if we can rewrite this series to be the sum from n equals 1 to infinity of -1 times 1 over n. And so this is the harmonic series just multiplied by -1. So this is also going to be divergent because p equals 1. So again, so you see how simple the p series is. You're just looking at the exponent for n. Sometimes we have to rewrite it in series form, but other than that, there is not much work. For example 6, we have, why did I leave out the n equals? So n equals 1 to infinity of 2 over n times the square root of n is going to be the same as the series from 1 to infinity of 2 over, so we have n to the first times n to the 1/2. That's going to be n to the 3/2. And because 3/2 are greater than 1, this series is going to be convergent because p equals 3/2, which is greater than 1. For example 7, we have 2 over the 4th root of n cubed. And again, I left off the n equals. I'm not sure what I was thinking. This is going to be the sum from n equals 1 to infinity of 2 over n to the 3/4. And this is going to be divergent because p equals 3/4, which is less than or equal to 1. And finally, for example 8, we have 2 over the 5th root of n to the 4th. You know what? Let's change this around to be the 4th root of n to the 5th, just so we get something different. So we're going to have the series from 1 to infinity of, now in this case, we're going to have n to the 5/4. Now again, because we just switched the 4 and the 5, we said the 4th root of n to the 5th. And now this is going to be convergent because p equals 5/4, which is greater than 1. All right, so that's going to conclude this video over p series and the harmonic series. Remember, the harmonic series is just the p series in the case where p equals 1, and that is always divergent. In the next video, we'll talk about the alternating series, absolutely convergent and conditionally convergent. And, you know, actually, let's add on one thing here. We're going to have so below example 8, let's add in one thing because we're going to need it for the next video. So we're going to call this the nth term test for divergence. All right, so say we have the series from n equals 1 to infinity of some sequence. We're just adding up a bunch of terms from some sequence. So this is going to be true. 1, if the limit when n approaches infinity of an is not 0, then the series from n equals 1 to infinity of an is divergent. And I'll show you why in we'll just make up some example quickly but beneath this. So again, if the limit when n goes to infinity for an is not 0, then the series from n equals 1 to infinity of the sequence is divergent. Now, an example of this is going to be, say we had the series, something very simple. So n equals 1 to infinity, we'll say 2n plus 1 over 3n plus 2. So if we list out the first handful, like say we list out the first 5 terms of this series. So when n is 1, we're going to have 3 over 5. When n is 2, we're going to have 5 over 8. When n is 3, we're going to have 7 over 11. When when n is 4, we're going to have 9 over 14 plus, and all the way out to when we keep, when n keeps getting larger, we're going to have 2 to the n plus 1 over 3n plus 2. So I want to show you something on the calculator that hopefully helps this make sense. So say we type in the function, so we're going to have 2x plus 1 over 3x plus 2. So think for a moment what you expect to happen when n is very, very large. And so now we're going to inspect this table. Oh, go to attempted to use a variable or function where it is not valid. What happened here? Y equals, oh, delete that. So now when we look at the table, so what we're going to do is change by 100. And so as we keep getting larger and larger and larger and larger, what happens, you know what, let's skip by 10,000 now. We basically get 2/3. So when n is really large, our fraction, all of these turn into 2/3. And remember from just taking limits in pre-cal and maybe even A2 trig and for sure in calculus, that the limit when n goes to infinity, if the degree of the numerator equals the degree of the denominator, the limit is the ratio of the leading coefficients. So the limit when n approaches infinity of 2n plus 1 over 3n plus 2 equals 2/3. Because when n is really large, then the 1 and the 2 don't matter. So at some point for this series, you're just adding 2/3 over and over and over again. So this series never stops growing. It increases by about 2/3 every time. And because this limit is not 0, then this series is going to be divergent. That's what we mean by the nth term test for divergence. If the limit of the sequence is not 0, then the series is going to be divergent. All right, so now that concludes this video. And in the next video, we'll talk about the alternating series and conditionally convergent, absolutely convergent. And we'll use these other tests to justify some of those things. See you next video.